Okay, good morning. Okay, quiet down, please. Good morning. Oh, that was really sad. Good morning. Okay, I'll accept that. All right, so I got the course calendar pulled up here. Let's take a look at what's going to happen in the next few days. Today we're going to cover two sections, 8.1 and 8.2. That'll be the last lesson that Exam 2 will include. Exam 2 will include everything from integration by parts up to what we are doing today. Friday we'll cover one more lesson, but 8.3 is not going to be on the exam. And you will be glad when you see it on Friday that it's not on the exam. Speaking of exam, it's coming up next Thursday after you come back from fall break. Sorry to ruin your break that way, but I had no choice. This is what they assigned us. Okay, and I'll talk more about the exam on Friday. All right? All right, so as you saw, we're going to look at two sections at the same time. So imagine you got a function whose graph looks something like that. Okay, so we know how to calculate the area under the curve. That we already know. It's simply an integration. Today we're going to ask a different question, is how long this curve is. Between x is equal to a and x is equal to b. Now, as you can see, if this is a straight line, then the question is simple. You simply connect the line between the beginning and the end, use the distance formula. But this is not a straight line, so we cannot do that. However, what we can do is to look at a short segment of this. And let's say this is the first segment between here and here. And we're going to approximate the curve there by a straight line to start. So let me blow up this region here. And here's what we see. We see a curved line here, and then a straight line. And if the interval is short enough, then this curve will be almost a straight line, and we can approximate the length of that by using a straight line. Right? So how do we approximate that? Well, it's pretty simple. We could use the distance formula, or we could use the Pythagorean identity, Pythagorean theorem. The horizontal distance here is how much you have changed x. Call that delta x. And the vertical distance is how much you have changed y. Right? So the arc length right there is roughly equal to the square root of delta x squared plus delta y squared. right? And what else can we do to that? We could factor out a delta x squared from underneath the root. Okay, so I took out the delta x squared from each of these two terms under the root. The first one becomes a 1. The second one becomes delta y squared over delta x squared. So now when you multiply this back, we get what we started with. And what I can do then is to factor this delta x outside. Right, so this delta x is outside the root. It was a square under a root. When it came out, it loses its square. So this will give us the approximate arc length of this little short segment. Then we repeat with the next subinterval. Until we reach the end. Right? So to the next one, the next one, the next one, and then add them up. So that's going to give us some kind of estimation based on short straight line segments. Yeah. It is. Thank you. Oh, that made it worse, didn't it? All right, so let's rewrite that. 1 plus delta y over delta x quantity squared delta x. Sorry about that. Okay, so that's an approximation. And we are, of course, not going to be happy with the approximation. But we want the exact length, right? And you know how these things work. We can make the approximation really, really good by shrinking the subintervals. That means after we do that, delta x will turn into dx, right? And delta y over delta x, what does that turn into when you shrink these things? Right, the derivative dy dx. Very good. And how do we sum up all of these after we shrink? We integrate, right? So at the end, what we end up doing, I'll call the arc length lowercase s, became an integration from a to b, and we integrate the square root of 1 plus dy dx squared times dx. So that's one form we can use. An alternate form here is if you go back a little bit to this thing, we could have factored out delta y squared instead of delta x squared. So this could be turned into 1 plus dx dy squared times dy. Okay? So here's the alternate form. I use different letters for the bounds because they would be different. So the first one is the most familiar one when we integrate with respect to x, going from a to b. The second one is the case when we're integrating y instead of x. And I'll show you an example of each. So y as function of x. And here, x as function of y. All right, so try not to memorize this formula the way it is. Try to think about how we got it by using short segments and then derive it when you need to get the formula back. All right, so let's try this on a few examples. Let's find the length of this curve. From x is equal to 0 to x is equal to 1. Okay, so let's kind of visualize what this looks like. It's not a simple one to sketch, so if you couldn't come up with a sketch, it's not a big deal. It starts at -1, right here. And it's got a shape that looks kind of like this. Okay, so it goes from -1, 0 to 1, about 0.9 when you're plugging 1 into here. And so here's the formula we're going to use, the one we derived just now. We obviously need a derivative, square that, add 1 to it, and then square root. It looks pretty complicated, but oftentimes this will end up being quite simple to integrate. Okay, so derivative. 2 radical 2 x to the 1/2. I need that squared. So I get 4 times 2, that's 8. And then x to the 1/2 squared is x. Okay, and then integral of 0 to 1, radical 1 plus dy dx squared, right here. Okay? And how would you integrate this? Substitution would be a good one, yeah. And I'm going to do the way where we also change the bounds so we never go back to x. And this will turn into 1/8 u to the 1/2 du. So in the end, we get this thing. This is a pretty straightforward part here. And you end up getting 13/6. Trust me on that. Which is about 2.17. Okay, so in general, we get this answer here. A good thing to do is to check to make sure this makes sense. We know whatever this is, it must be longer than a straight line connecting these two dots. Which turned out to be, using a distance formula, roughly 1.9, roughly. Okay, so that's a good thing to check. Whenever you do this kind of problem, you get an answer out here. Compare that to the straight line segment connecting the beginning and the end. Whatever you get must be no smaller than that, right? The minimum this arc length can be is the straight line. If you get a number smaller than that, then you screwed up somewhere. Go back and check. So arc length must be greater than or equal to straight line length. It'll be equal if it's exactly a straight line, but in general, it should be somewhat bigger than that. Questions on this? Okay, good. Now let's look at one example using the alternate form. The one where we're integrating y. Generally, what you want to use this formula, the first reason is when the curve is describing x as a function of y. Right, that's a pretty obvious reason. When you're given x is equal to something involving y, that's a pretty good reason to do it. The second reason is when dy dx fails to exist. In at least one place. In order to calculate the arc length using the previous formula, dy dx has to exist on the interval a to b. If at some point dy dx fails to exist, this is a form that you can consider using. And dy dx fails to exist for many reasons, and one of the reasons is when you have a vertical tangent line. So dy dx, the slope of the tangent line becomes undefined, so therefore it does not exist. And here's an example where such a thing happens. The curve is y is equal to x over 2 to the power of 2 over 3. And we want to know the length of that from x is equal to 0 to x is equal to 2. Let's check out dy dx first. So this turns into 2 over 3 times x over 2 to the power of 1/3. And that thing is downstairs. Okay? And now you see, dy dx is undefined at x is equal to 0, right? So therefore, the previous form can be used. And if you sketch this out, you'll see the same thing. Right over here, tangent line becomes horizontal, so dy dx doesn't exist. And therefore, that form can't be used. So we have to go try the other one, dx dy. Even though dy dx doesn't exist, dx dy can still exist. It doesn't guarantee that this is still applicable, but at least it's worth a try. Okay, so what I need to do is to rewrite this equation here. The dy says that we have to integrate in y, so we need to rewrite the equation x as a function of y, and then use the alternate formula. And let's see, how do we do that? We can raise both sides to the power of 3/2 and then multiply by 2. And also, because we're going to y now, the original bounds apply to x. They no longer apply to our new variable y. Okay? So we need to adjust that also. When x is equal to 0, y is equal to 0, of course. When x is equal to 1, y is equal to 1/2 to the 2/3. Oh, I'm sorry. Yeah, I'm looking at the wrong thing here. Original bounds with 0 to 2. I'm sorry. That's right. That's right. I was looking at the right thing, but the wrong number. Okay, so when x is 0, y is 0. When x is equal to 2, y is equal to 1. So that's simple. Okay, now the formula looks the same as the other form, but we need the x dy, which is the derivative of this with respect to y. And we get 3 to the power of y, 3y to the power of 1/2. And you got to check, does it exist from 0 to 1 for y? Well, yeah, right? It's always defined. It's 0 at some point, but that's okay. But it's defined. Defined everywhere on our new bound. Okay, the rest of this becomes pretty simple to do. The arc length, using the new bounds in y, 0 to 1, radical 1 plus dx dy squared dy. So that's 0 to 1, radical 1 plus 9y dy. And you integrate using a substitution again, and I'll skip that step. We end up getting about 2.27. That's the arc length. All right, so that's when you can use the alternate form. In general, the original form is probably the most convenient one to use because we're used to taking derivative y with respect to x and integrating in x. But there are two instances at least when you want to consider using the other form. Questions? Good? Okay, good. All right, so that's the arc length. Not terribly difficult. Let's look at something that's related to that, and that's going to give us the surface area of an object. So now imagine we have the same curve. And we'll consider that curve from A to B. And now let's go back to the revolution thing. Let's revolve this around the x-axis. So we'll end up getting something like that. Okay? And we already know how to calculate volume, right? You have two methods for doing that. There's the disk/washer method, and there's also the shell method. This time, what we like to find is the lateral surface of that object rather than the volume. Okay, so imagine this thing here, and then just look at the surface of that. And you want to calculate the surface area of this object. And one good way to think of that is to also think about if this thing is not solid but hollowed out with just the outline, and if you flatten it out onto a flat surface, how big is that surface you just flattened out? All right, so here's the way we're going to do that. Once again, we're going to consider a short segment somewhere on this graph. Let's say from here to here. And if I revolve just that short segment here, so just a very short segment here, and what do you end up getting? It's not, well, it's a disk, but we want to look at just the outline of that. So it's kind of like a little ribbon, if you want to think of it that way, a little circular kind of thing. Let me sketch this up a little bit bigger. And I'll exaggerate the, so it's not to scale, but something like this. And what we want here is not a volume, but we want the surface area of this and all the way around. Okay, can you visualize what we're doing here? Yes? Yep? Okay, so if we can find out this little short ribbon here, then we know we can just integrate to find the rest of it. So that's the challenge that we have to overcome. Now what this is, think of it as a cone with part of it chopped off. Right? It's exactly the same shape. It's part of a big cone with a big chunk of it removed. Anybody know what this is called? There's a name for this thing. There's at least one name for this thing. It's called a conical, not comical, it's not funny at all. That's a joke, by the way. It's called a conical frustum. It's part of a cone that you removed a portion of it. And it has two radii. We'll call the smaller one R1, the bigger one R2. And we'll call the length of that slanted side, we'll call that L. So look up a geometry book and you can find out the volume and the lateral surface area of this object. And it turns out to be pi times the smaller radius plus the bigger radius times the length of the slanted side. Okay? Okay, so that's how you calculate a general frustum here. Now we want to apply that to this frustum laying on its side. So what we need to do, so this is the axis of revolution. And the smaller radius right here, this is some number y1. Let's call that y1. And the bigger one here is some other number called that y2. So that's the length from here to here, and then the length from here to here. What about L? What's that? What did you say? The arc length, exactly, right? This L here is going to approximate the arc length. Okay, so this gives us a clue on how to calculate this. We need to know the radius at the beginning, the radius at the end, and then arc length, and then use that formula. All right, so pi times R1 plus R2 times L. My blue marker is dying, so we're going to use black. It's going to be roughly equal to pi times the, I'll call that radius 1 plus radius 2 So that's at the beginning. Of the subinterval, and that's the end of the subinterval. Right? Look at that picture there. And then L here is the arc length. And once again, we're not happy with approximation. We want the exact answer. So again, we're going to shrink the subinterval. What happens when you shrink the subinterval? What happens to radius 1 and radius 2? If we shrink this small enough, roughly the same, exactly. And in this case here, what symbol would you use to denote that? Well, what is it? How do you find the radius? So what's the distance from the x-axis to the curve? Y, yeah, exactly. Yeah, good. Okay, so this thing becomes 2y. So pi times 2y. And arc length, we covered that just now. Radical 1 plus dy dx squared dx, right? So in this case, the lateral surface area, the book uses capital S. I'm not going to do that. I'm going to do just surface area. A to B, 2 pi y radical 1 plus dy dx squared dx. Okay, so this formula is much more difficult to recover from basic geometry. So on the exam, if you need this formula, it will be provided, but you have to know the arc length. I believe you can recover the arc length, but this one, I'm not going to make you memorize that. And just like in the case with arc length, sometimes dy dx fails to exist, or the curve is described x as a function of y. So an alternate form you could use is this. Notice that even though dy dx turns into dx dy, that y outside remains y. So let me make this very, it's important distinction here. Okay, so these are the two forms you could use if you're revolving this about the x-axis. If you're taking this about the y-axis, then the radius becomes x when you're measuring this going about the x-axis. It does remain dy dx and dx. Okay? Look in the book how this thing shows up, but trust me, that's the formula. And like I said, I'm not going to make you memorize all of these forms, but you do need to know just the arc length. Okay, let's do one example just going about the x-axis here. If you get the idea there, going about the y is simply changing the formula just a little bit. We'll use a simple shape. Y is equal to radical x. X is bounded between 1 and 2. And we're taking this to go about the x-axis. Right? Let's take a look at what this looks like. What does y equal to radical x look like? Describe it in words. Sideways parabola, which half? Upper half, right. And we just want a segment of that. So something like that, let's say. And then we're going to take that to revolve this thing. Right? And we want the just the lateral surface area. So think of it as almost half a sphere with the cap chopped off, and you're looking for the surface area of what's left. And that's what we need to use here. We know y, simple. We just need dy dx, and then that's basically it, right? Okay, dy dx, derivative of x to the 1/2, 1 over 2, radical x downstairs. Square that. We get 1 over 4x. Okay, and then you put this into that formula, we get surface area equal to 1 to 2, and 2 pi y is equal to radical x. And then we have this thing here, 1 plus radical, under radical 1 plus 1 over 4x, and then dx. How would you integrate this? Yeah. If I start at 0, yes. But if I start at 1, then I don't have that issue. That's a good point. If I had started doing the calculation at 0, then at the beginning, the derivative fails to exist. I have to switch to the other form. Yep? So excellent point there. But we are in the safe region here, so we should be OK. OK, so what you want to do here then is to simplify or combine the terms under the radical, like that. And what that's going to allow you to do, radical of what's downstairs here is 2 radical x. And that's going to let you cancel out the radical x and integrate something that's far simpler. Let's see, the 2's also cancel. Let me take the pi out. 1 to 2, radical 4x plus 1 dx. And once again, you integrate this by a substitution, just a plain U substitution. And once again, I'm going to omit that step. Just go directly to the answer. So here's what the answer should be. You should verify this for yourself. It's not a pretty number, but it is what it is. All right, so as you can see, this is based on the arc length here. That's usually going to end up being the tricky part. If you could handle the arc length reasonably well, then the extra y here can potentially pose some issue, but you can integrate this using all the methods that you've learned so far, by parts substitution, possibly trig substitution, but there are ways to get from here to here. Setting it up is the part we want to focus on for now. All right, that's it for today, and exam 2 covers up to this lesson, okay? And I'll see you on Friday.